So yes, we will talk about post-quantum cryptography. The goal is, for those of you who haven't really heard of quantum or of cryptography, or have just basis in math to be able to understand it. So I will start with just easy reminders. So in cryptology, we have two main fields. So it's cryptography and cryptanalysis. In cryptography, the goal is to protect the data by using encryption methods. And with the correct key, you can later decrypt your data to use it. And in cryptanalysis, the goal is the opposite. So from the protected data, we want to mount an attack to retrieve the plain text data. And the whole goal of these attacks is to be able to do them not only theoretically, but also in practice. So we have a threshold in cryptography to make a difference between what we will consider attacks that can be done in practice and attacks that cannot be done in practice. And the threshold is based on when we estimate to be the cost of the best attack possible. So if the cost is too high, we will estimate that the attack is not possible in a real world. So what we call the cost of the attack is the number of computer cycles we have to do to achieve the attack. So for example, with a computer, you have in the order of magnitude of 1 gigahertz. So it's 1 billion operations per second. So that's approximately to the power of 30. If you use this computer for 1 year, you have approximately 2 to the power of 25 seconds in 1 year. And if you use 1 million computers for 1 year with at least 1 gigahertz, you add this 2 to the power of 20, so you get 2 to the power of 25 in total, and you keep a margin to be certain. And so we estimate that above 2 to the power of 80 computation cycle required for your attack, that you cannot do it in the real world. For more secure purposes, for example, banking or army stuff, you may want a threshold at 100 or 128, for example, to be more secure, have a higher margin. So our cryptographic scheme, we can study them, and we rank them by how efficient is the best known attack. So for example, all the schemes we use today, all in green, have the best attack against them that is above 80. And for our same scheme, for example, RSA, we can have multiple parameters. For example, the length of the operators. So we can have multiple RSA scheme with bigger parameters, so bigger security in total. But here, for example, we take a higher parameter, but we lose 8 times the efficiency. So in order to have the best efficiency, but still is being secure against attacks, what we do is we choose often the schemes that's the closest to the security requirement to have the most efficiency and the required security. And so what can happen in cryptography? There are two main things that happens with time. It's the technological improvement. So for example, right now, AT starts already to be quite obsolete because computers go faster than 1 gigahertz. Maybe it starts to be cheaper and cheaper, and the power to compute with 1 million computers starts to be lower. So we can use more of them. So with the time, and for example, the Moore's law and every technological advance, we have to consider that attacks can do more and more computation to be achievable. And so we have to sometimes forget some of the previous cryptographic scheme and go to the ones with bigger parameters or new ones. But the second thing that happens sometimes in cryptography, it's the apparition of new attacks. So an attack, what it does basically is to bring the security requirements, or the number of cycles of the best attack, it brings it lower. And that's where quantum computers have changed everything in cryptography in the past few years. So quantum computer, to talk a little bit about them, we hear a lot about quantum computer in the media. We have movies about them. We have a series about them. We see them a lot in media in general, and it's sometimes hard to know what is possible, what is not possible. We hear teleportation. We hear about a lot of things. What we just should know for cryptography is we have well known of what can be done with the computer was a quantum computer. But what the physicist can do right now is far behind from what we speculate could be done in the future. So we have a large gap in terms of time between what we know theoretically and what we can do experimentally. But what we know theoretically already allowed us to create quantum cryptography. So, for example, there's the name of one of the most well-known schemes of quantum cryptography. In these schemes, there will be a sender that will choose a specific polarization for its specific state for a quantum particle. And the receiver will read it in a special basis, and sometimes that will give information if the basis were right, and sometimes not. But with this table, the sender and the receiver can exchange a key. And the big advantage of this quantum cryptography scheme is that it's proven by our by our laws of physics that there's no possible interception of this key. We can make this exchange as secure as we want. But right now, these schemes require perfect experimental conditions. So it's a very, very short distance. It was made in lab. It was done for real, but it was in a very good experimental conditions. And from now, we are really far to be able to do it, for example, for cell phones or for portable applications. But it gives us an upper limit on what we can do in terms of security, because when we can use our quantum computers to exchange with, for example, this scheme, we know that we can have a security as high as we want, with a complexity linear to the security requirements. So that's a very, very good key exchange. Quantum cryptography, basically, it's the end of cryptography as we know it. We can protect our data by using this method. But there's also the quantum cryptanalysis that happened, and two big things in quantum cryptanalysis. So the first is the possibility to Fourier transform way faster than we can do classically. So, for example, it's used in a Shor's algorithm for factoring. So factorization was really important for Diffie-Hellman and RSA constructions, but right now the attacks that require the quantum Fourier transform can be done very, very efficiently. And the other big change is the complexity of finding one given implicitly in a list. So if I give you a function that has only one possibility of giving the output 1, classically, you would have basically to check every possible solution until you find the one. But with Grover's algorithm, you don't have to check everything. You just have to check the square root of the number of possible values. So that's a big speed up. So to wrap up, we have an exponential game for Fourier transform. So some algorithms which were exponential go into the polynomial domain. So some attacks starts to be really efficient. And to find the index of a 1, which basically means in cryptography a brute force, because it's just finding the correct key that allowed the encryption. For this, we divided by 2 all the security requirements, or the security of a brute force is halved, basically, with this. So the effect on our cryptographic schemes, it's a big shift to the left of the screen. And after the quantum computers come, we expect to have this distribution, or even more to the left if we discover new things. But what's to note is that 95% of our currently cryptographic use for asymmetric cryptography, for example, is totally vulnerable post-quantum to the attacks. Hopefully, we still have symmetric cryptography and hash functions that can be reused. We will have to have slight adjustments. For example, AES blocks will have to be bigger, 256 instead of 128, for example. But that's a slight modification that is already planned in AES, and the hash function will have to be bigger. But all the asymmetric cryptography we have right now will have to be changed. So to sum up this part, we have theoretical models and theoretical attacks in the 1980s and 90s. So we know that once we can build a quantum computer, we will have quantum cryptanalysis. But the start of cryptanalysis will be far sooner than the apparition of quantum cryptography, since right now no one can really believe to have very soon, for example, a quantum cell phone. Right now, that's not. We don't think about it as a possibility for the near time. But there's a need in all this gap of time for post-quantum cryptography. That means cryptography that resists even to a quantum computer. So what we are doing right now in this very moment is standardize a post-quantum cryptographic scheme. So we choose it right now. Maybe we will use it only later, so that when quantum cryptanalysis is possible, we are secure. So what is standardization? Standardization is a big international contest. So every team of cryptography in the world can propose its own scheme. And every other team in the world will try to find attacks on this scheme to keep only the ones without vulnerabilities. And among the ones for which vulnerabilities are not found, we'll try to merge those who are too similar and to eliminate those who have lower performances than the one that other ones still in the contest. And with different steps, we managed to have right now a third round of the contest, of the standardization process, which contains only 4 contenders. So all the focus for cryptography right now is on these 4 schemes. So I will talk a little bit about them. So to talk about them, I will use this little color code. So I will put the advantages in green. For example, the date of creation is really important in cryptography, since a cryptographic scheme that is older is, I would say, more secure, in the sense that more people already tried to break it. So we know that it's been 40 years that a lot of brains had tried to break Michaelis and had not managed to do it. So we think as it as a harder problem, maybe, that Kyber, that just began 8 years ago, and maybe just not enough people who tried to break it to find a vulnerability. So in these schemes, what we can compare also is the different size of keys and of ciphertext. So for the keys, we can see, for example, that Michaelis have huge keys. That's a very big problem for if we have a space constraint, for example. Andrew has the smaller keys, but it was designed to have the keys as small as possible. The ciphertext is very good for Michaelis. That's how you read this table. And we can also study the performances. So the number of cycles for key generation, encryption, and decryption. And we can see that Michaelis, for example, have a very, very slow key generation because the keys are very big, so it requires a lot of computation. and Kyber was designed to have a very, very low times, very big efficiency, basically. So it would seem to be a very, very good contender, but the security proofs for Kyber are not at the same level that for the three others. So maybe it's not the best contender. So the choice is for the NIST to make. So we will learn. I think the deadline for official standardization is 2023, I think, given by the NIST. So by then we will know which post-quantum solution we will have to use. But what we can see in this table that there is quite a lot of differences in all the scheme. But what's also very important to see is that behind the schemes are some cryptographic problems that are in common. All the schemes are in a way quite the same. So for example, the three last schemes are based on the problem called learning with errors. So in the learning with error problems, you are given a lattice, that's the gray lines, and you are given a point in the plane or in a space. It's not in dimension 2, but your task, the problem, is to find the closest point, the closest vector, the closest intersection in the lattice to this point. So that's called the closest vector problem, or the LWE problem. And quite similarly, McEllis is based on error correcting code, on code cryptography, code-based cryptography. And the problem is quite the same. You have code words here in red, and you are given a node, and you want to find the code word closer to this node. So it seems to be quite the same problem, and that's for a very good reason. It's two instances of one same problem that resists to the quantum computer. That's the hidden subgroup problem. So I will just take 2 minutes to explain it using math, but I will give an example right after, so don't panic. So we'll take a public group. So that's a group of many elements, as you may know the definition in math. We'll take a subgroup that we will keep hidden. So the name hidden subgroup problem. And the goal is to create this function. So we will project our space on the subgroup. So see, if we take an element and we project it, we get a new element that we call it colorize it. So we assign it a color. For example, if I take an element 0, I could have the color red, and if I take an element 1, I could have a color green, for example. We use colors because it's just elements of a set. There's no operation you can do in colors. You cannot add colors or multiply colors. They're just basically bit strings. And this hidden subgroup problem says you create this function as a black box. This black box is hard to invert. So what we know is that even for a quantum computer, as soon as the G group is non-abelian, even a quantum computer finds this problem hard to invert. You can have pairs of inputs and outputs and not find the hidden subgroup. So the example, we will take one of the simplest non-commutative groups. For example, the groups of rotations and symmetries of 2n polygon, 2n-sided polygon. And what we will do, oh, my slide is frozen. Okay, we will project our group on a subgroup. So the subgroup will be given by a symmetry axis, and our colorization function basically gives for every pair of symmetric nodes a color. And what is hard in the hidden subgroup problem is if I give you this function that from a certain point gives you his color, you cannot easily find the axis of symmetry. So that's a problem that's hard to do even for quantum computers. For example, in the MAC-LAAS cryptographic scheme, what is done is just a parity of a certain vector, so it will alternate. And you can see that, for example, if you wanted to find this axis of symmetry, basically your only hope would be to find two consecutive edges with the same color. So that would be one of the best nodes we can think of right now to find this axis of symmetry. So that's the mathematical basis for all post-quantum cryptography. But for standardization, there's a lot more to study. There's not only the mathematical requirements, there's also a practical requirements, because there's not only computational attacks that you can do on a system. There's a whole other class of attacks that are possible. We call them Sidechannel Attacks. So the most well-known ones are timing attacks. For example, in RSA, you can know according to the power consumption, according to the time, if you are dealing with a 0 in your secret key or with a 1 in the secret key. So that's been a long time that we know this kind of attacks, but we have a solution to not be attacked this way. Is we code in cryptography in a very special way. We don't code for efficiency. We code in order to be constant in time. So that means I cannot have in my code if that depends on a secret value. Because if I have two branches of code that depend on the secret value, the different durations of these branches will leak about the secret value. That's the same for every 4. I should not code with my incrementation depending on my secrets. That's something you should not do for cryptography. And other thing you have to do for cryptography is to code with always the same elements in the same place of your memory. Because if the address of one element depends on the secret, you could sometimes have one element in one level of cache, for example, and other times in a separate level of cache. But the time you have to retrieve your data up to the CPU leaks about which level of cache it was before. So it may leak about the address, and if the address depends on the secret, then you leak information about your key, your message, or something like that. So what it causes us to do is to always code basically in the worst case scenario. We cannot benefit of if this bit of the secret is 0, then I can do no computation. No, every time I still have to do every computation possible, even if it's a computation just on a row of zeros, just to spend the same amount of time. So this causes low performances in order to not being subject to timing attacks. But there's a whole other genre of attacks. That's power or electromagnetic field attacks. So basically, the simplest way is to put probes in your chip, directly physically in your chip, and do measures on them. And with this, you can get values, for example, of your keys. For example, power analysis. There's some that are due on AES that allows to guess one round key. That's not enough to break AES, but we know that these attacks really exist for known cryptographic schemes. So what we do for standardization is we try to propose a solution to have lower impact of power or electromagnetic fields attacks. So we put all our cryptographic computation in a coprocessor. That's let's say a separate chip near to your processor. Every time your processor had to encipher or decipher a message, it sends it to the coprocessor. And this coprocessor is designed to have the lowest leakage possible. For example, the best coprocessor right now for post-quantum cryptography is, I think, one made for Saber, the Saber protocol for post-quantum cryptography. But there still is leaks that happens in this. For example, the element of Cyber who leaks information is the number generation. It is a very specific random number generation, and according to which side of the distribution you will not get the same the same power consumption. So so it leaks information, and the two ways to block side channel attacks are right now a big subject in cryptography, because a new standard in cryptography that is very weak to side channel attacks, it would be a very big problem. So there's a lot of research going on this right now. And so we know, given what we know of quantum computers, that our schemes in cryptography will be insecure. We benefit of some gap between theory and practice, so we can choose post-quantum cryptography, and we standardize the post-quantum cryptography right now. So we have 4 finalists that are very different in performances and what they can do, application domains. But the mathematics behind these 4 finalists are very much similar. This is the hidden subgroup problem on non-abelian groups. So if you ever think of one new scheme, one way to check if it's post-quantum, it's to check if it's a variant of the hidden subgroup problem for a non-abelian group. And more than just this mathematical side, there's also the physical side, so the side channel attacks, timing attacks, and power and electric magnetic attacks. For this, we have ideas of ways to bolster against these attacks, but there are still very big problems with them, so it's a big field of research. I will just conclude. Pierre-François asked me to talk a little bit about what I do actually in my thesis, to give you an idea of what can be done now in post-quantum cryptography, for example. What are different leads we can have? What are different subjects we have? The main one is the easiest one, post-quantum cryptography, because it has to resist to a more powerful computer. It's slower and often bigger in terms of keys. So one main focus is to do optimizations. That's a very big thing in crypto right now. Some things that are more in our lab only is to find a more generic approach to the hidden subgroup problem, because right now all the cryptography is based on error correcting codes or learning with errors, but there's no generic post-quantum computing cryptography model. No, so that would be a great thing to have to maybe generate more efficient cryptographic scheme in the future. One thing we do for optimization and with the goal to help McElis to be standardized is, since we remarked that McElis, the big bottleneck of the schemes is the level of parallelism you can give it. So we thought of that, and we came to the conclusion that we could use some processing in memory tricks to have a very high parallelism. So we call it cache computing, because some people found a way to compute, for example, a Boolean operation in the cache. So that allows for very high level of parallelism. And so that solves the biggest problem for McElis right now. That is the time for key generation. And so we also have a whole focus on side channel attacks. But we don't really believe in coprocessor. We want to find things that would be cheaper to implement than adding a coprocessor specialized in cryptography. So maybe the cache computing solution would be a very good idea, because since we move less data between the different levels of cache and we compute in cache, we save a lot of time, of energy, and by saving energy, we lower the signal and noise ratio that someone could study with the probes in a chip, so that leaks less information. And another possibility we have would be to voluntarily include errors in the computation, so that every physical measure that is made have a chance to be a measure of a wrong value. So overall, the attacker cannot infer as easily information about the secrets. And the final study that we can do is to find expressivity that was lost in the transition into post-quantum cryptography. What I mean by that is we had, in the classical setting, a lot of what I would call fun cryptography, like identity-based encryption or attribute-based encryption, basically cryptography that could solve more general problems, such as sending a message to someone. And some people already found how to do it in LWE post-quantum cryptography. But for example, they did not find how to do it in code-based cryptography. That's one thing we lost in the switching into post-quantum cryptography. So we try to find it again right now. So I hope you enjoyed this presentation, that you had an idea, that you have now an idea of what is post-quantum cryptography, what is to come in the upcoming years, what would be the biggest change. I wanted to thank you everyone again to have listened to me, and I would be glad to answer any questions.